Okay, hello everybody. Let me get started here. I want to introduce myself. So my name is Stephanie Weirich. I'm a professor at Penn, and for the past 13 years, I've been doing a lot of work extending the type system of the Glasgow Haskell Compiler of GHC. So today I want to talk to you about what we can do with those type system extensions, and specifically dependent types in Haskell. Now, how many here have used Haskell before? Yeah, oh, great, great. Right, and so if you've used Haskell before, maybe, like me, you appreciate that its mathematical character, that it comes straight from the lambda calculus, right? But ever since I was a little girl and I found out about dependent types, I kind of wanted more from this language. But there's just not a pi in Haskell, right? Nobody can use a pi type here. So what do I do about it? Right? Well, I add a pi type. No, I add a whole bunch of language extensions, mostly to increase the expressiveness of the type system. And I'm gathering together a whole bunch together that I typically use. Some of them, the ones in red are ones that I've worked on, the ones in blue are others, and they all kind of work together to give something that I like to call it dependent Haskell. Because when I program with these language extensions, I feel like I'm programming in a dependently typed language. All right, and so I want to explain how that works to you, and I'm going to do that by showing you an extended example of what I consider to be a dependently typed program written in Haskell. Right? So you might be wondering, why do all this? Why do you want to have dependent types in the first place? Right? And there's lots of reasons. The reason for today, motivating my example that I'm going to show you, is because we want the type checker, Haskell's type checker, to know about our application, to know about our domain that we're working with. We don't want the type checker to just help us rule out general purpose bugs. We also want the type checker to rule out domain-specific bugs. All right, so let's look at a domain. So here's just a simple little domain I've worked out. It's just a simple example just to show you. I'm not saying you should go use this library, but I want to walk through how this library can take advantage of dependent types. So it's based on regular expression capture groups. So you might have a string like this, and you might define a regular expression to recognize this string as a file name or file path. And you might use some capture groups to pull out parts of it. Right, so we might look for the base name part of the file path and want to find out. You parse it into that string. We might find an extension that may or may not be there. We might want to look for some directories and find out what all of the directories are in the path. So I've written a little library that will do this for a regular expression. It's loosely based on how capture groups work in other languages, though most of the time, other languages won't give you multiple answers, but I wanted to show that off. And the important part, where do types come in? The type system, we're going to get our result from our matching. It's going to be a dictionary. It's going to tell you, the base name is this, the extension is this. The type system should help govern that dictionary access. So let me show you how it works. Oh, I knew I would do that. Let me show you how it works in practice. So let's go over to Haskell. So here is a little module that is using my library, right? And right here, this is my regular expression that has the capture groups that I'm going to be using for parsing this string right here. So let me walk through the regular expression for you. Regular expressions are more complicated than dependent types. Okay, so between that pipe and the other pipe down there is the regular expression itself. Maybe we start with a beginning slash. Then from this paren to here, this is for the directories. And I adopted Python's way of naming capture groups. So question mark P dir, this is the name of the capture group. Inside of it is a regular expression that is supposed to be what a directory name looks like. We could have multiple directory names, so we have a star outside of that capture group. Here's the base name, so from this paren to here, we're again capturing it with a group named base. Here's the regular expression for the base name. There's only one base name. Here is the extension. We may or may not have an extension, so we have a question mark, but it's named X. And it's anywhere from the last dot. Okay, so that's the regular expression. Here's the string, and let me go down a little bit. Here's the line that is running my function that matches that regular expression against that string. And I know it's going to succeed, so I'm going to course, it's going to give me a maybe. You know, it could fail, but I know it's going to succeed, so it's going to give me a dictionary. And then here I want to access the components from that dictionary. Right? I want to pull out what is the base name, what is that list of directories, and what is that extension, right? So let me just show you that this works. So we can go, I have it loaded, I already loaded it into GACI, but I can say, okay, there's the base name, there's the directories, there is the extension. Now, those of you coming from Python or JavaScript, you're not impressed. Right? You do this all the time, right? So let me show you something you can't do. Let's try to access a field that's not in that dictionary. So I didn't name anything in the regular expression named F. I'm just going to call, let's uncomment that, and I'll reload. All right, and now I got a type error. And here's my type error. Right? My type error is telling me that I just can't do that. That dictionary, the type of that dictionary is tailored from the regular expression. It knows exactly what kind of capture groups are available, right? Base, dir, X are the only capture groups. Since I asked for F, it's going to refuse to compile my code. That would be a bug in my program, and so it has found a bug for me. Right? And my library has allowed me to even customize. GHC has a mechanism for customizing the type error messages, so I can even make sure with my domain-specific type system, I have a domain-specific error message going on. Right? And even back up here, notice what's going on with X and Y and Z. So, oh, I have to make it compile again. But right? It's able to figure out that X, Y, and Z all have different types. I don't know if you can see down here. It's showing the types of what these variables are that the type checker has inferred, right? So Z, the extension, it's optional. So maybe it's going to be a string. The list of directories is a list of strings, right? There are no type annotations in this program. The library has figured out how to determine this information. Right? So this is that's what I want to do. That's what I want dependent types to do for me. So let me kind of unpack this a little bit and show you how that works. Okay. All right, and I'm going to unpack this by asking this question, When we say dependent types, what do we mean? Because Haskell's not a dependently typed language, clearly. Yeah, and so I've kind of taken the idea of dependent type systems. What do dependent type systems provide? And isolated 4 different things that are related to each other. But there are 4 different capabilities that your type system can provide, and that this example is taking advantage of, that I'm using to implement this library. So then I'm going to walk through each of these 4 capabilities and kind of explain why it's important to this example and what is going on in GHC to support it. All right, so the first thing is I want to program the type checker, right? Right? You saw that somehow I had to tell the type checker about what capture groups are in regular expressions, right? And so I was using the type system to implement this domain-specific compile time analysis. All right? So that's what I call type computation, being able to program in your types. And it really is programming. So here I have my regular expression. And I didn't show you this, but I could. We could ask GHCI, what's its type? And this is actually what it would show you. The type of this value is a very informative type. To be able to do that, to check that dictionary, it has to know quite a bit, right? So it knows that it's a regular expression. But this regular expression type is this huge component here that I'm calling an occurrence map. Right? This is just a list of mappings from the capture group name and something that's called an occurrence. It tells me how often that group could get captured by that regular expression. You know, maybe by the base name, it only gets captured once. Maybe we might capture it many times, like the directories, and maybe we may or may not capture it, right? Right, so this information is what the rest of the system is going to use to govern that dictionary access. Right, and the Haskell has type-level lists and strings. They're called type-level symbols. This is a promoted data type. This is a normal Haskell data type that I'm using in the types. Right, just like an enumeration. Right, now, how do we get from that term to this type? The first step is a little bit of template Haskell. So those of you, you might have recognized that these brackets invoke template Haskell, which is some compile time metaprogramming. All it does is it invokes a parser for regular expressions that I've written. So at compile time, it runs the parser, and it translates that regular expression string to this bit of code, right, which is another way of representing the abstract syntax of a regular expression using some constructors for this regular expression type that my library creates. So we have, this creates a regular expression that only accepts a single character. This takes two regular expressions and creates a sequence of it. This one iterates the regular expression, right? It's just parsing into the abstract syntax in the first step. And then the compile time type reasoning, that compile time programming, all happens in what the types of those constructors are. That's where the real magic is, because what happens is template Haskell parses, produces this, and then the type checker runs. Right? And all of these operators have very informative types that can compute this type for this particular expression. So let's look at the types of those operators. Right? So some of them are pretty straightforward, right? The regular expression that only matches the empty string doesn't capture any capture groups. Right? So I'm just using an empty list as its occurrence map. It's saying there's not going to be any capture groups from here. Right? Things get a little more interesting when we build up regular expressions. So if we make an alternative regular expression, right, you'll see that we're going to have some occurrence map here. It's going to capture some groups. That's going to capture some groups. What groups does the entire regular expression capture? Well, that's defined by this type-level function that I have written. Right? This type-level function takes these two data structures that the type checker is manipulating, runs the function, and computes what the alternation is going to capture. So again, I'm going to go back to GACI and kind of show you how this works through example instead of walking through what those functions do. So down here, so mark is the one that says this is a regular expression that should mark a substring to create a capture group. Right? So if you look at RA and RB, right? RA down here captures 1A, captures A once. RB captures B once. It doesn't really matter what regular expression it's using to match it, but it knows that it's matching a B. What if I do an RB and then an RA, put them in sequence together, right? Then the function that I wrote for rseqed, for its type, merges those two occurrence maps together. It also sorts them. So I have a uniform representation of those occurrence maps. So it's sorting, it's a lot like a merge sort. All right, what if I alternate? So think about if I here on the right side have RB with an RA after it. What if I said either that one or just an RA? How many times is that going to capture RA? An A. How many times is that going to capture a B? All right, well, Haskell figures that out, right? It's always going to capture an A, but it may or may not capture a B. Right, if you can see here, A is once, B is optional. Okay, what about a star, right? So here, if I have R star, I want to iterate, I want to do 0 more occurrences, right? In this case, we don't know how many times we could get an A or B. We started with doing A or B exactly once, but we could do it many times, and many includes 0. Okay, so we have these functions, and they run with the type checker to calculate these occurrence maps. Okay? Right. Okay, now what do we do once we have those occurrence maps? Right? Well, that's where the next idea comes in. We're using those occurrence maps, these description of what's going on with the capture groups, we're using that to constrain values. And this is what I mean when I say index types. The RE, this regular expression type, it's an index type. It's indexed by this occurrence map. And that occurrence map is going to, it's going to make a huge difference for the type checker, right? So when we have a regular expression that's indexed by a capture group, if it successfully matches, it's going to produce a dictionary. And the dictionary type is going to be indexed by exactly the same occurrence map. Right? So when I match RE, then I'm going to produce a dictionary that has exactly the same map. Right? And then what does that tell me about my dictionary? Right? I'm indexing that dictionary type by this occurrence map. That tells me a lot about that dictionary, right? Because the way I've set up the dictionary type, it's going to force the structure of the dictionary to look something like this. Now, maybe it's going to be different strings, but it's always going to be an entry with a string for base, an entry with a list of strings for the directories, an entry with an optional string, a maybe string for the extension, and that's it, and nothing else. From the type, I know at compile time what the values of this type must look like. Right? Not any arbitrary sequences of entries. It's something that matches this pattern. Right? And that's good. Right? On one hand, note what's missing from this value. There's no keys. Right? Base, dir, and ext, they're not stored with the values. Why? That's kind of redundant. We already know what they are. We just look at the type, right? And the type is going to tell us if we need to look up things in this dictionary. It says, okay, go do the first thing. You know exactly where to go at compile time. So at compile time, my library tells Haskell exactly how to access the base component. So that get field at base, that's resolved at compile time. And that's important that it's resolved at compile time, because when I start asking things that aren't there, that's how I can have a compile time error message, right? If I ask for a field that's not present in that dictionary. Okay, now how is it that we go from this type to knowing exactly that it has this structure? And here I'm using an extension to GHC that's called GADTs. It's a generalization of the algebraic data types in Haskell, and you may have seen in other languages. They look a lot like normal data types, but they're indexed, they're indexed by other types, and that index is allowed to change in the constructors. So dictionaries are indexed by occurrence maps. If we have a dictionary indexed with the empty map, it must be the empty dictionary. It can't be any other dictionary. If it's indexed by a non-empty occurrence map, right, so if it's indexed by an occurrence map that looks like this, maps this symbol to that occurrence, right, then we have to have an entry for that symbol and that occurrence. And then whatever the rest of the dictionary is, we have to have more of that, right? So defining the type in this way is how we establish that constraint. Okay, now let me show you a little bit about how the entries work. So entry, here's something that has an entry type. This might be an entry for an extension, right? The E is the constructor for the entry type. Here's the value that that constructor is going to carry. This is not the only type that this expression has. Notice how the extension, it's here in the type, it's nowhere in the value. We could give lots of different types, but I happen to have given this type to this value, right? And when I create an entry, it's another index type. It's a type that's indexed by these two things, right? The name of the capture group and the occurrence. But in this case, the really important thing with this entry is what type of data it holds. And that type of data is calculated by this type level function that I'm calling octype. Right? This octype function, it takes one of these occurrences, and it's going to map that occurrence to the type of data that should be stored in that entry. So the second index here is constraining the type of data. So when I have opt, then the octype for opt says, I need to have an optional string value there. And that's the only kind of string value. That's the only kind of value that can be stored if the index is opt. Okay, so we're using these index types to make very strong constraints on what our data looks like. Okay, now the next thing we're doing, now this is something that I'm calling double duty data, right? What does that mean? Right? I'm actually using data in my program in two different ways. I'm using it in the type indices, but sometimes I need to use it at runtime. So let me show you where we end up doing that in this library. Right? So here I have this dictionary. The type tells me what it looks like, and let's print it out. And so we can print it out, and Haskell prints it out. Okay, why is this weird? Well, when you print something out, there's no types at runtime, right? Haskell erases all types before it runs your program. Where does base come from when we're printing it out? How does it know what type of value to print, right? That's where we actually do have to somehow preserve the types to runtime a little bit just to be able to do things like this. All right, and so if we were in a dependently typed language, like Idris or Agda, this is where pi would come into play, right? I would write a function, for showing a dictionary. It would need to call a function called show the entry for me, tell me how to take one of these entries and turn it into a string. And it would have a pi type, right? And the reason it has a pi type is because we need to quantify over the key and the occurrence, right, for a particular entry, mapping a key to an occurrence. But then we also need to use the key and the occurrence when we're printing it out. We need to call a helper function that's going to show what that key is. And when we show the data, we need to know what the occurrence is to know exactly how to show that data. Right? So for example here, show data itself has to have a pi type, because it's going to show the kind of data for that entry, and the type of it is octype O. We need to interpret that to a type, right? And so we need to match here and say, okay, if the occurrence is once, then we need a show function that's going to convert our string to a string. If it's opt, we need a show function that's going to convert a maybe string to a string. And if it's many, we need something that's going to work for a list of strings. If you're a Haskell expert, you know that all of these functions are actually called show, but the example gets really confusing if I just put show, 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 right? We need to figure out that we have a show function for each type of data. And so we have to do this pattern match in order to do it. But we're in Haskell. We're not in Idris. We're not in Agda. We're not in Coq. How do we don't have a pi type. Right, so here's where Haskell uses something that's called a singleton type. Right, so a singleton type is a way of connecting some type level data to runtime data in a tight enough connection so that we can kind of do the same thing. Right, so here I'm showing the definition for a singleton type for my occurrence information, and you can see that for each of these variants of the occurrences, I have a corresponding data constructor that matches it, right? And S_once, the singleton for once, is the only way I can get something of that type. And so what that means here, when I'm matching on S_once, that tells me what O is. That tells Haskell what O is. So we know O is going to be once, so we know octype once is going to be string, so we know this is the show function that we need. So this is really the only change we need to do to make the code that we wanted to write actually work. We had to draw in these singletons. And here I'm using the singleton library. I put this code in italics because the singleton library can actually generate this definition for me. It's pretty mechanical. OK, so the last bit that shows up when you're doing dependently typed programming is equivalence proofs, some kind of proofs of equality. And the reason this shows up is we're working with these really rich types. They have computations embedded inside them. The type checker is asking this question all the time. Is this type equal to that type? Well, it needs to ask, is this computation equal to that computation? That's a hard question for a type checker to answer. It can get pretty good at it. Right? Type checkers are pretty good about reasoning about equivalence, but they're not perfect. They can't be perfect. So sometimes the programmer needs to step in and be able to help the type checker reason about that equivalence. And that happens here in this example. Right? So I'm going to dive in more to the implementation of this library. I showed you we had these constructors like rseek. They're actually these smart constructors. They wrap the real data constructors for my abstract syntax of regular expressions. The real ones, they have the same types as the smart constructors. The smart constructors do a little bit of optimization before they actually create like a sequence regular expression. Right? So this makes my code a little bit more efficient because we can, as we build regular expressions, we don't need to put in, like for example, if you said, okay, first match the empty string, then match something else. Right? That's the same as just doing the second thing. Right? That doesn't change what the regular expression is. There's several different identities on regular expressions. We can take advantage of that. Right? But how does this type check? Right? We have these index types around, right? And when we get to this line, the type checker actually has to do a little bit of proof, right? Because we said the result type of this function is the merge of the two arguments. But we're providing R2, which just has this type. So we need to know that the merge is equal to S2, but we have the additional information that we know S1 is empty, is an empty occurrence map, just nil. And the type checker can do this, because it can look at the definition of merge, and it knows if you merge in an empty list, it doesn't change. Right? So just from the definition of merge, it can figure this one out. So sometimes the type checker works. Sometimes, though, you have to give it a hand. So here's another example. So this is another one of my smart constructors. This is for the Kleene star, where we're going to iterate a regular expression. And the last case, we're just going to call the R star constructor. But we have two optimizations that we want to look for. Right? If you iterate the regular expression that matches an empty string, that's the same as matching an empty string. 0 or more empty strings matches an empty string, right? So for this line, though, for it to type check that optimization, the type checker has to do this little proof that says if you didn't match anything, if your occurrence map is empty and you repeat empty, it's empty, right? And empty is just nil, so that first case tells us exactly what we want. This is our definition of how repeating things works for these occurrence maps. What about this case? Here we're going to be repeating something. Now, okay, what is this? If you repeat something that's already been repeated, that's also the same as if you just do it once. Right? So we're getting rid of 2 stars in a row. Right? So to do that, we go to the type checker. Here, this is something that the type checker can't do for us. Right? Here we need an identity that the type checker doesn't know. And here's the error message it gives. If you, when I was developing this, I got to this point and I got this type error message and it says, Stephanie, I couldn't figure this out. Right? I couldn't figure out, well, repeat s is equal to s under the constraint that s is equal to repeat s1. Well, what is it telling me? Right? It's telling me it can't figure out that if you repeat something twice, that's the same as repeating it once. Now, I can go and I can look at this definition. I say, OK, what does repeat do? It goes through every single one of these pairs in the list, and it turns the occurrence to many. Right? We're under a star. We don't know how many times it's going to happen. What if we do that twice? We're just going to turn all these manys to many again. Right? So that's true. Right? So that's something that we want the type checker to be able to prove that. We could sit down and do a little proof, but how does the type checker do that? Right, so in this case, I need to tell the type checker that, and so I'm going to get the type checker to prove it for me using the type class system. So I'm going to make a class of occurrence maps. I'm calling it WF for well-formed occurrence maps that satisfies exactly the property that I want. Right, so an occurrence map is well-formed if you repeat it twice, it's the same as repeating it once. That's exactly the information type checker needs. Okay? Now I have 2 kinds of occurrence maps. I have empty ones, and they're well formed. And the type checker can verify this case. It can say, yeah, empty maps are well formed because it plugs in the empty map there. It reduces the repeats. Empty is equal to empty. Great. Here's my inductive step. I say an occurrence map, right, is well formed if the tail of it is well formed. It turns out Haskell can do this automatically too. I have to guide the induction, I have to provide it with an induction hypothesis, but that's all it needs to be able to show it for this case as well. Right? That's it, that's my entire proof. Right? And then I need to get that reasoning to the right place. And so I had to go back to my code base and add just some well-formedness constraints to wherever I needed it, both to that data type for regular expressions, but also for the smart constructors, right? And so when I'm doing this, and I get to this case here, in my context, I have the information that the type checker exactly needed. And so this time, it just goes through automatically. I don't have to do anything to explicitly apply this proof that I did. It is the type, the class resolution has fished it to exactly the place that I need it to. It's fished it everywhere, but the type checker can find it. Now, this wasn't the only proof I had to do. When I was finishing my library, I had other things, you know, ralt, rseek, they did some optimizations too. And so I needed 2 other properties, right? And so I already had the well-formed class, and so I added the new properties to it. My proof didn't change. These were also properties that were true by just very simple inductive arguments, right? So I was able to add those properties, and then they were available where I needed it. Okay, so what have we seen? Right? I've tried to kind of point out where we're doing things like dependently typed languages in Haskell. So what does that mean? How does Haskell stack up as a dependently typed language? Right? So let me just kind of go back through all 4 of these things that we've seen and kind of compare what's going on in Haskell versus what's going on elsewhere. All right, so we started with type computation, and here I want to argue Haskell's really good for type computation, right? I showed you, like the example I showed you, it was using some of these operators that allow you to write functions and types. We have data to use those type functions. It looks a lot like functional programming, except everything is capitalized, right? That wasn't the only way I could have done it. I could have also, the parts I didn't show you did a lot of type-level computation based on the class system using class resolution. And these two things can interact with each other. And that's exactly how that domain-specific error message works out and that compile time resolution for that dictionary access. So it's great that these things work together so well. And they also work together in a context where we didn't really have to care about termination, right? Haskell, even if the functions that we're writing at the type language, we haven't proven that they terminate, we know Haskell is still type sound. Okay, what about index types? Well, something like GADTs has been in Haskell for over 10 years now. They're pretty mature. There's been some recent extensions that improve the support of GADTs so that now, with the last type in type thing, there's fewer and fewer AGDA examples that we can't go and write in Haskell. Here, we don't have a pi type in Haskell, so here I'm going to say it's OK. We had to fake that example that we wanted to write with a pi type using singletons. It worked well in this example that I showed you. It doesn't always work well. Singletons can sometimes really clutter up your code. Some of my current work, I've been working with my collaborator, Richard Eisenberg. We're working to actually go put a real pi type into Haskell. And then finally, for the equivalence proofs, here, things is more like the Wild West. There's lots of different ways to do it. It's not clear what's the best way to do these equivalence proofs. I showed you one way based on the type class system. There are other ways you could do it based on type-level programming. You can try to do it more like how AGDA and Idris and Coq approach equivalence proofs, but Haskell's logic is much weaker, so it's not quite the same. GHC also provides something I didn't show you called solver plugins, where you can just throw in a special domain-specific solver for the kinds of equivalence proofs that come from your application. Or you could skip all the equivalence proofs if you want by adding axioms or by creating a phantom type. Right, so it's not clear to me what the best way forward, but there's lots of fun things to play around with. And really what we're doing when we're in this domain, we're doing program verification. That's always a hard topic. And the more that we can do here, the more exciting it is. Okay. So I'm just going to wrap up with that and kind of thank you for your attention and hope that you're convinced that we're doing some really fun things with dependent types in GHC, and I hope you'll be able to play around with it too. If you want to see the full example, I put the full example on my GitHub. There's a repo, DTH, for dependently typed Haskell. That's where I collect examples like this one and others of fun things that you can do with dependent types in Haskell. I also want to thank a lot of my collaborators who have worked with me on these extensions to Haskell over the years, and especially the National Science Foundation that has provided a lot of the funding for my research over the past couple years. Okay, so thank you.